Hello, everyone. In this video, we're going to look at example 7 on the notes and examples from section 3.1 on the definite integral. So for this example, we are told to use rectangles to approximate the area under the curve, and then use technology to find the exact area. So first, let's use the method that we've seen before for approximating area using rectangles. So what I want to do is get a sense of what this graph, y equals 5 over x, looks like. So to get a sense of the shape, we can first ask, what is the general family of this type of curve? And we see that the x is in the denominator here. So this is a rational function. So it'll have that hyperbolic structure. We see that when x is equal to 0, the function is undefined. So we will have an asymptote at x equals 0. And then we see as x gets larger and larger, so as it goes to infinity, then what we get is a smaller and smaller number. 5 divided by a huge number gets smaller and smaller, so y equals 0 is also our asymptote. So to kind of fill in what this graph looks like, let's plot a few points. So let's plot the output values of our function at 2, 3, 4, 5, and 6, just to get a sense of what our function looks like on that interval from 2 to 6. So let's plot those points. So when x is 2, y is 5 over 2. Let's clean this up here. All right, so when x is 2, y is 5 over 2, which would be 2 and 2 halves. We go into 2 and we plot 2 and a half. So we can do this with 3, 4, 5, and 6 to plot those points. So what I'd like you to do is pause the video and determine all of those points on our curve. So find those y values for when x is 3, 4, 5, and 6. So when you do that, you should see that your y values look like the following. So take a moment to pause the video and check your work. And then go ahead and finish the curve of that graph. And we can just worry about that first quadrant. We do have another part of our graph down here, but for us, we only care about our function on the interval from 2 to 6. So that's what we want to focus on. All right, so from here, let's go ahead and use rectangles to approximate the area. So how many rectangles do we think we will want to use? We see that our interval has a length of 1, 2, 3, 4. So let's go ahead and use 4 rectangles. And then we can use either the left endpoints or the right endpoints. So together, let's go ahead and do the left endpoints. And then I encourage you on your own to try out the right endpoints just to give you more practice with this method. So what we will do is use left endpoints. With 4 rectangles. So for us, our width change of x is going to be 1. We use 4 rectangles here. And that was because it makes the most sense if we're looking at an interval that has length 4. And we see that also happens if we say it takes 6 minus 2, the length of the interval itself is 4, divided by 4 total rectangles gives us a width of 1 each. So here, n, total number of rectangles is 4. So now what we want to do is compute the sum from I equals 1 to 4. And don't worry too much about this notation. But just to get a sense of what we want to do, we want to add up change of x's times f of x sub I. Where for us, x sub i's are going to be those endpoints on our rectangles. So that would be 2, 3, 4, and 5. So let's go ahead and write that out. So we'd have width of 1 times f of 2 plus width of 1 times f of 3 plus 1 times f of 4 plus 1 times f of 5. So lucky for us, we already computed those values f of 2 is just 5 over 2. F of 3 is 1 over 2/3. It is exactly those y values that you found here. So we can just read those off. So our first term, in fact, we don't even need to worry about that 1, recall, because our width is 1. So when we multiply, we can just drop it at this point. So our output values here, f of 2 is 5 over 2. F of 3 is 5 over 3, or 1 and 2/3. F of 4 is going to be 5 over 4. And then f of 5 is 5 over 5. So go ahead and take a moment to pause the video and add up these fractions. And I encourage you to use your calculator and then get a decimal answer in the end. And when you do that work, you should be getting a number around 6.417. So just to recap here, what we've just found is the area under these rectangles. Awesome. So now what would the definite integral look like if we wanted to compute the area under our curve y equals 5 over x from 2 to x? So I encourage you to pause the video and write out that definite integral first, and then we'll look at what it looks like together. So we have our long curly S here for the integral symbol, and our limits of integration are from 2 to 6. So we decorate our long curly S like that. And then our function that we're integrating over is 5 over x. And that's just that output value of our function. And then we're differentiating with respect to x, or the widths of our rectangles are along the x-axis. All right, so now I want us to use a calculator to actually compute explicitly what the area under the curve is. That is, compute this definite integral. So go ahead and follow along with me. Go over to your Desmos graphing calculator. So you can do this by going on your web browser, or maybe you have the app downloaded on your device. So that's what I have here. And now I'm going to show you how we can actually compute that integral. So if we go over here, lower left corner, and click on that ABC, we're going to get a keyboard here. So I'm just going to start typing integral, INT. And right away, all I need is INT for a little integral symbol to come up. Now I'm going to go back to my number, so that lower left corner again, and I'm going to put in the bounds of my integration. So the lower bound is 2. Then I'm going to click up to this upper bound and put in 6. Then now I'm going to input my function. So that's 5 over x. Like that. And then I'm going to finish with a dx. And I don't even have to press enter. It knows that I'm finished, and it gives me the value of the integral. So we see here 5.49306,144, etc. is the area under the curve, exactly between 2 and 6. So we can write that on our notes. Use Desmos to get exactly, well, we have to round up, 5.49. So we see that our estimate was a little bit of an overestimate, and that's because we're using these left endpoints in this case, which give us a little bit extra area for each computation.